This is the stator of the machine, right? We're going to do what? Short. What did I measure here? I measured the open circuit voltage, right? Here I'm going to measure the unshort circuit. Right, this is the ammeter here. It's going to measure the short circuit current. Now, again, the machine is rotating at a synchronous speed. Keep in mind, it's rotating at synchronous speed. That one should be there. We are rotating with another prime mover. We are connecting it here, and we are rotating the rotor at a synchronous speed. The excitation system is open. You have to be very careful. You know, the excitation system is open, and here is shorted. So, what kind of voltage you are going to see over there? Almost zero, right? A very, very, very small voltage, or almost zero. So you are going to see a little bit of current, but it's going to be very, very small value because this voltage is very small voltage, right? The voltage is very. That's the EAF over there. Again, if you look at it, EAF is this circuit. You know, we are shorting here. We are shorting here, right? We are shorting here. So this EAF, which is equal to this much, ideally, if IF is 0, EAF is going to be 0. If we have a little bit residual flow, but let's see, even there is no excitation, you know, in the system, the breaker is open, still you see small voltage and a small current. But let's assume that one is 0. I'll say why I'm saying let's assume that one is 0. Now, carefully, you make sure you put a big resistor here. A big resistor here. You close this switch. What is going to happen? You close the switch. What is going to happen? You're going to have some IF, right? So we are going to have some back EMF here. We're going to have some EAF over here. If you look at that circuit, we're going to have some EAF, right? So as soon as we have the EAF, you know, RA and XS, they are small values. The RA is very small and XS also is small, but bigger than RA. So we are going to have some current, right? If you don't put a big resistor here, what's going to happen? The machine is rotating with synchronous speed, right? And you generate a big voltage, like a rated voltage. Think about it. I mean, big voltage, not you're seeing 10 times, 20 times of the rated voltage. But for example, rated voltage. If you have a rated voltage here, right, and it's shorted, you're going to see huge current, right? You're going to kill the machine. Exactly like a transformer. When we did the short circuit test, we said we short the secondary of the transformer very, very carefully. We bring up the voltage and we look at that current, ISC, right? Our short circuit. We start to reduce this one slowly and we monitor this current. To make sure this current is not more than rated current, right? The current is going to go up, up, up. We keep it maybe 5% or 10% more than rated current, not more than that. And we stop the test very quick. You know, we are not going to keep it for 10% for like 10 minutes because that one also is going to make the machine to become very hot, right? But you do this one because you want to have a little bit more information. You can go a little bit over the short circuit current, right? Sorry, rated current. So here, if you plot the current, I'm going to plot I short circuit, right? I'm going to plot I short circuit versus what? IF. Like here. Sorry, like here. IF, right? So this one is going to be like, this is going to be a linear curve because the machine is not going to get saturated. Why? Can you tell me why machine is not going to get saturated? So always we had this bend things because machine gets saturated, right? Why machine here is not getting saturated? We cannot go to the, see, the saturation happens somewhere, this is rated, right? It happens somewhere here, right? It's going to be maybe around here, not even past this point. Because if you go bigger than this one, it's going to kill the machine. The machine is shorted, right? We're going to have a, even if we have a 30% of the rated voltage, it's going to be too much to kill the machine. It's shorted, right? So basically, the voltage is going to be pretty linear, right? If the voltage is linear, short circuit current also will be linear. Because short circuit current is going to be EAF over RA plus JXS, right? Or it's going to be EAF over square root of RA to the power of 2 plus XS, right? So if RA is fixed, XS is fixed, basically if EAF is fixed, not fixed, EAF is linear, right? The current is going to be linear. So that's the reason the short circuit test is going to be like this. The curve is going to be a linear curve. Now, you measure this one, and you make sure you don't go over the short circuit current, that much. So let's say this is the IN. When I put N, I mean nominal, and this is the for example 1.15 N. If you go here, I think this one is going to be about 0.2 IFN. I call it IFN or something. I'm saying 10%, 20%. I don't know exact number. It's going to be different from machine to machine. Maybe 10% of the rated current for field current for the synchronous machine. Compared to here. Here, if you look at it, this is the IFN. This is the IFN. The nominal excitation current, which is going to generate the nominal voltage, right? Here, it doesn't have to be that much. Even with 0.2 IFN, you're going to get there, right? And keep in mind, this curve is linear, right? If I want a 0.5 IFN, I didn't test it with that way, Because I'm not doing that testing, right? But if I want more, I can continue this step, right? It's a linear, right? So, but as I said, in the lab, we don't go over this one. We get a few points here, we get the line. If you need more, just we extend the line. You know what I'm saying? We don't test it with the, 0.8 IFN, something like that, because it's going to kill the machine, if you do that. So, we did the short circuit test, and we did the open circuit test. Now we're going to go back to calculate the XS. Let's see how we can calculate it. Because RA we calculated already. We know how much is the RA. We need to calculate the XS, right? If we calculate the XS, we have the parameter of the machine to solve it. Let me put it in the middle. Now we want to calculate excess. I think calculation, because we use the short circuit and we should use the open circuit test results, and we calculate excess. Let me draw those both here together. Before drawing this curve, let's see how we can calculate, and after that I'll draw it, you can understand it better. Let's say RA is 0, because this is usually a smaller than this one. Let's assume RA is 0, right? Can you tell me how much, and here is shorted, for example. Can you tell me how much is the excess? Can we say, let's say a square root of xs to the power of 2 plus RA to the power of 2 is EAF over current, whatever is IA, right? This one is going to give me the value of this one, right? So basically, I know how much is the RA. If I ignore RA, XS is going to be equal to this, right? And if I don't ignore RA, so basically XS is going to be more IA to the power of 2 minus RA squared, right? It's going to be something like this, right? But as I say, you can assume this one is 0 almost. Basically, it's going to be EAF over IA, right? So you can see if the machine is shorted, and I know how much is my current and how much is my voltage, I can calculate my XS, right? Now let's go back to this guy. VOC. That's coming from VOC. This is the IF. And let's put this one here. I short circuit, right? Remember, most of them, they were versus IF, right? Just I put them in the same curve. This is the air gap line, right? And let's assume this one is 0. And we had OCC, right? Right? This is this one versus this. The other one is, usually this one, the slope is much smaller than that. And this is for this curve. This one is related to this axis. These two, they are related to this axis, right? And I put them in the same origin. I plot them in the same origin, right? Now, what did I say? I said, if I want to calculate XS, assume RA is 0. Because we don't have to go through this equation to calculate. And we know EAF is equal to VOC when the machine is open, right? Circuit, right? Now I'm going to say this way. Hey, it's better to calculate it with the nominal voltage, right? So let's say, if I will have, I'm going to use the air gap one. Vn, right? Vn, V nominal, right? Let's find out how much IF I need here. Let's call it IF1, right? This IF1, how much short circuit is going to generate? ISC1, right? So as we assume the machine is not saturated, right? So I can use the air gap line. If the machine is not saturated, I can use the air gap line, right? So if I want this much voltage generated in my machine, I have to have this much of IF, right? So this much IF is going to give me this much I short circuit, right? So now let's go back. If I have this much IF, right? How much EIF I'm going to have in the open circuit, with the open circuit, right? And how much, if the circuit is shorted, how much current I'm going to have in the circuit? That I still want, right? So basically, we call it XS, let's say, unsaturated. Is it on or not? I'm not sure what's unsaturated. XS. You call it on or not? I'm not sure. You guys know. On? Okay. Unsaturated, you know, synchronous impedance, XS. I'm calling it unsaturated because I use the air gap line. Keep in mind, that's the reason I'm using it unsaturated, right? I use the air gap line. How much XS is it? Somebody tell me. I call it Vn. Over. Just, I'm not sure, did I put the line voltage here or open circuit? We'll look at this from example, we'll see. I think still they use a line voltage here, you know, when they put this one in. So if it's line voltage, I should put this one divided by s square root of 3, right? But right now what I put here is based on, I put here phase voltage, this is the phase voltage. But I need to check the book to see what they are using. They maybe use the line voltage, you know. If it's a line voltage, you only should divide this one by a square root of 3. If it's line voltage, just you put a square root of 3 here because you need to go with the phase value, right? So basically you can calculate excess like this. This is unsaturated, if the machine is not saturated. Now let's calculate the real excess. Real excess is going to be different for every point, right? Right? But let's calculate it here. If I want to calculate the real excess in this case, if I want to have a Vn, right? It's not going to be this much back. I exaggerated here to get to the saturation part because I want to show you here. But usually these two, they are not this much different. They are much closer to each other. But let's say this much. This one is going to generate IF2, right? And this IF2 is going to generate ISC2, right? Right? The real IF I need to generate Vn is IF2. Which this IF2 is going to generate how much? ISC2 short circuit current, right? So saturated XS is going to be how much? Vn right? They call it XS sat. Sometimes they put the sat here. Sometimes they put the sat here. It's the saturation. It stands for saturation. What do you see here between XS non-saturated and saturated?
Saturated smaller.
Exactly. Why? You can see for the same voltage, the current is here, right? So we see here, XS sat is less than XS. Then I put XS means non-saturated, you know. Or you can put the index for it to say non-saturated. So we can calculate XS like this. Usually, using XS is accurate enough. We don't have to get to the saturation part. Unless we give you the curve, then we can go calculate exactly how much is the XS. So this way you can calculate XS, we calculate the RA. Now you have all the parameters of the machine. So you know how to solve it's like induction machines, like transfer. We have all the parameters of the machine. You know how to measure the P mechanical, you know how to measure the P core loss and those kind of things. So everything is known for the machine. The next thing I want to go over, I think we can cover this one also. Let's cover this one. What do they call it? This is Persian, I need to translate it. What's it called? Power characteristic? No, not power characteristic. Power characteristic. Power equation for the machine. Power equation for the machine. Let's go there. You know, I'm going to make it very simple. What do they call it? Call it R and X. I'm not giving it even name of X or RA. I have an X and R, and here I have an E1 with an angle of delta, and I have an E2 here with an angle of 0. Right? After that, we can apply this one to this circuit. You can see here, E1 for example could be EAF, right? And E2 could be VT, right? But just I'm putting it in general terms to see what it is. The power equation of the simplification.
Did you just make it? Did you just translate it?
Yeah. No, I said over there. I said characteristic of power angle. Yeah, that's the really like it. Characteristic of power angle. You know what I have here in this course. But I have it here in English. It's the power angle. So let's go through the equation quickly here. I call this one I1, right? Let's call this one I. I call this one I. And look at here. We have a P1 plus JQ1 coming from here. And P2 plus JQ2 is going to, right? As I said, I'm going to use all these things for synchronous machine later, you know. But let's go through this equation. So I want to calculate the P, Q, P1, Q1, P2, Q2, all those kind of things based on the R, X, E1, E2, and delta. We're going to calculate those things. So how much is the current in this circuit? R plus Jx, right? That's a simple circuit. The difference of the voltage divided by the impedance is going to be let's call it R plus Jx. Let's call it Z with it's going to have an amplitude of Z with a